Hello everyone and welcome to today's webinar on directional overcurrent testing with SVERKER900. Speaker for today's session is Mr. Ali Hussain, who is an application engineer at Mega Middle East. So before handing the mic over to Mr. Ali, I would like to highlight a few points. You all are being muted to avoid any disturbance during the presentation. Do park any question you may have for the Q&A session at the end or share it in the chat window. All questions will be answered at the end of the session. Also, we have come up with a Mega exclusive Middle East page on Facebook and LinkedIn. I will just share that in the chat window. You can go on that link and you can just follow us for regular updates. Also, we have upcoming webinars in November and December. So you can just go on the link I've shared in the chat window and you can register yourself for the upcoming webinars. There will be a small survey form at the end of the webinar. So please do fill the same for the feedback regarding the webinar. The recording will be sent to you in 2 working days through the GoToWebinar system as a standard process. So I now hand over the control to Mr. Ali. So let's get started. Over to you, Ali.
Thank you very much, Sanjay, and welcome everyone. Good morning, good afternoon, wherever you are. I hope you all are safe. So for our topic today, or our agenda today, basically, if you are joining us also from the last week webinar, the Freja 500 directional overcurrent relay, some of the things here will be redundant for you. Please stay on until the end, since in the end we will do a practical session on the SVERKER900. If you are new to this webinar, you have not attended last week webinar, first I will give a quick introduction about overcurrent and why do we need a directional overcurrent in our protection systems. Then I'm going to talk about what things that you require to be able to enable directional overcurrent in your system and why do you need these things or these requirements. After that, we are going to talk about some of the details of directional overcurrent, like the maximum torque angle or relay characteristic angle, nowadays they call it, and how it's forming your directional overcurrent area or criteria. And then we're going to talk about how do we conduct testing based on this information or a testing concept. And the end, again, we will do a practical session using SVERKER 900. So please tune in and stay until the end with us for the practical session. So as a start and as a beginning, in any protection systems, there are 4 criteria that you need for your protection system to work as effective as possible. These 4 criteria start with reliability, meaning you have a system that you can depend on when you need it. It will be not active for a very long time, maybe in years, until a certain fault happen or a fault happen, any fault happen. This protection should be ready and be able to detect that fault and clear it automatically. Now, even with this thing, having a dependability that you can have on your relay, also you should have security, meaning during this whole long period of non-operation, if there is no fault, there should be no operation, meaning what we call mal-operate should not happen when you have a reliable system. After that, you have selectivity, and basically it is having to isolate only the faulty part to minimize the downtime or the down area as much as possible. And this selectivity is in most cases what we desire to have, but sometimes not be able due to some constraints in cost or in performance. Then we have sensitivity. It's basically meaning that I should be able to sense any fault and detect it, whether it's small, huge fault, or a small fault. And last but not least, speed, meaning a fast clearance to any fault type to minimize any damages or harms that happen to your power system. Sometimes you have to compromise between speed and selectivity, or vice versa, to get an optimal performance from both. Our session today is mainly about overcurrent protection. It's the most basic and most simple and easy one to configure and to apply to your power system. It's the most cheapest. It requires the least minimum requirement to apply this type of protection or principal protection. Basically, it's set a current value, and once you exceed this current value, your relay should operate, whether it's instantaneous operation or time delay operation. It really depends on your configuration or coordination between your upstream and downstream protection system. In some particular cases, having a directional element attached to your overcurrent protection enhance your performance and give you a better selectivity, or even sometimes better speed of a clearance a fault with using just the addition of a directional element. So where do we need or how can we benefit from overcurrent in a radial system, for example? We can just put a time dial or time coordination between different sections of my line or radial line to give me a good mix of reliability, selectivity, and speed of fault clearance. So the question is now, where do we need a directional overcurrent protection? There are a lot of cases. This is just one case I am going to explain. It is a parallel line configuration. When you have a parallel line configuration in your system, and you don't have a directional overcurrent relay, you have a non-directional overcurrent relay. The protection system, if a fault happens on one of these lines and you have a time coordination between these two sections or these two buses, the fault current, if there is a fault on line 2, the fault current will go through both lines to reach this fault. And in this case, you will have relay 2, relay 4, and relay 3 all operate because they are non-directional, and thus you lose both your lines, line 1 and line 2. Even though line 1 is a healthy line, it doesn't have a fault, but because you have time settings to coordinate between relay 1 and relay 3, this misperformance happened. How can you correct this operation? Is by adding a directional overcurrent to relay 3 and 4. So now they only operate towards their respective lines. So relay 3 will only operate if the current flowing or the fault current is flowing through line 1, and relay 4 is only operating if the current is flowing through line 2. In this case, when the same scenario happen again, relay 3 will see the current flowing in the opposite direction and will not operate. Only relay 4 and relay 2 will operate, and thus clearing the fault in line 2, giving me a better selectivity than the first scenario. This is just one example where directional overcurrent can help you get more performance and a better selectivity. How does a basic principle of operation for directional overcurrent? Basically, we look at the direction the current is flowing in. It's either forward or reverse. So it's either coming out of the bus bar or into the bus bar. Now, in AC signals, you know that the current flows in and out, or it's alternating between positive and negative half cycles. Because of that, we cannot just measure the polarity. So in order to get this direction reference, we need to look at the phase angle of the current. And since we are talking about phase angle, we will require a reference. The best reference that we can use is a voltage input. That's why it's required to have a VT connected to your directional overcurrent relay. Without a VT, you will not have a phase reference, and you will not be able to detect the phase or the current direction. Now, under load condition, if you go and measure the phase angle of your current with respect to your voltage, you will find it a very small angle, like between 7, 10, 5, 9. It really depends on your load condition. This is a normal condition, but when a fault happen on your line, the condition changes and your load becomes your line impedance itself. So because of your line impedance is highly inductive impedance, your phase angle of your current in the forward direction, meaning current coming out of the bus to the line, your angle will be in the 60 to 90 degree range. So 75 degree will be a mostly angle of in this range for your fault. And because of this, we can detect or predict where this forward line angle can happen. And respectively, if you have a fault on the back of your line, or in the reverse direction we call it, where the current flow to your bus, your angle will be shifted 180 degree from your forward angle. And using this principle, we can build our directional overcurrent element. So how do we do that? We use something called characteristic angle or relay characteristic angle. Previously in electromechanical relays, they used to call it MTA, or maximum torque angle. In this maximum torque angle, we use reference like V1 voltage for this angle. And as previously, we know that the fault current is lagging, or the voltage is lagging the fault current by 60 to 90 degree usually. So we can really predict where this fault current will happen and draw a characteristic angle near it. But as you know, this fault current or location could happen anywhere on the line. Thus, I cannot just predict one line to be my fault line. So I will open a whole area, I call it a blinder, to consider this as my forward area, and anything outside of this area will be my reverse area. Now, a lot of relay vendors and relay manufacturers use similar concept to this. Some of them are making this area slightly smaller, creating a no operation area in the middle between the reverse and the forward, but that's not really a big deal for us. Since in your relay configuration, you will either have a non-directional, a forward directional, or a reverse directional setting in your relay. And also you will be setting your MTA, or maximum torque angle, or some relays call it RCA. So this angle, I am using it now with reference to V1. The question raises itself now, is a V1 a good reference for fault happening in I1, or is VA is good for faults happening on IA, or IRED is good for fault happening in VRED? Well, the question here is, what is the best reference voltage to be selected, or reference voltage selection? When a fault happen near your source or near your bus bar, the VT will see this voltage very, very small because it's seeing like a short circuit in front of it. So this thing lead us to having a poor magnitude or unreliable magnitude and phase angle of my voltage input. That's why it is better to use the other phases for reference for your respected phase. So for I1, I will use V23. For I2, I will use V31, and so on. And for face-to-face faults, I will use also the other phase, the healthy phase, as my reference for my voltage. So when I have here my phase to neutral voltages, I also face-to-face voltages, and my I fault here, I'll create my MTA angle with the reference for IA with the reference to my face-to-face voltage instead of my respective volt. So this MTA for phase A. So I can use this as a reference V23 with my MTA to get a better reliability when I have fault near my source. Since in that case, V1 will be very small and is not so much reliable. And for the other phases, respectively, if you are asking, we just shifting 120 degree. So for I2, I'm using V31 for I2, and this is my MTA. And for I3, I'm using V1 2, and this is my MTA for that. So respectively, I'm using the other phases as my voltage reference, thus giving me the most reliability and least problem. And this is very important for us to understand because most of the commons relay are using this configuration. You will not be able to understand or test them without understanding this voltage reference very carefully. So if anyone have any question, please write that down, and later on we'll answer any question regarding this reference voltage selection. Now for the testing concept, if I want to test this directional overcurrent and I have my MTA angle known, my reference voltage known, I can basically do the normal testing, the pickup test or the timing test, which people used to do. But I need to make sure that my phase angle of my current is within the area of my forward region in case my setting is in the forward region, or in the reverse in case my setting in the reverse region. But if I want to test this actual region or this actual blinder, I need to test this minimum and maximum angles. And in order to test that, I need a test equipment that can change the phase angle of my currents or voltages. Clearly, you can use both. And test the pickup or directional pickup, we call it, for this minimum and maximum angle. And basically is by changing the phase angle from outside my operating region to the inside, slowly increasing it until we get inside and see when exactly this angle is operating. And the same thing for the other angle as well. I will increase the angle until my relay start operate or give me a pickup contact inside from it, indicating that the operation has begun in this relay. So for SVERKER900, just a quick note for it. It's using the 0 to 360 lead directional mode or phase angle mode. Some other test equipment will use different phase angle mode, but it really does not really matter for us. Depends on the test equipment. For this, if I have an angle in this first quadrant, it will be between 0 and 90, the second between 90 and 80, and the third will be between 180, 270, and the fourth will be 270 and 0. For any fresh graduate from university, these things will be very simple for them, but for people who are working in the field for long years, this basic concept might be need some refreshing just for understanding. Now, our testing example, I have my camera ready here with me, and the setup is a Micom B142 relay with a SVERKER900 connected in the respective way. I'm connecting all my 3 current channels and 3 voltage channels. I have my start contact indicating the timer has started, and my trip contact connecting to binary input 1 and binary input 2 respectively. And the relay that I am having, Micom B142, have the following setting. I have a pickup value, at which value the current will start operating is at 1 amp, and a time curve, indicating that I have inverse characteristic at a time setting 0.4, which is something we can do and test, but not really the main point of this webinar. And the direction of my setting is in the forward direction. The RCA, or the maximum torque angle, is 45 degree. Note that this IED or relay is using the following reference voltages, which most relay are using, but just for reminding, I have for I1 we are using V23, for I2 we are using V31, for I3 we are using V12. Our blinder is opening plus and minus 90 degree. So just a quick show of the setup. I have the setup here with me. I have the relay and I have my SVERKER900. Once we go to the actual testing part, I will explain every part in the device and how to do that. So in order to understand how we can test the phase angle, first I need to inject current above my pickup value, above 1 ampere, in order to eliminate that variable for us. So 1.2 amps is enough to overcome that. Second, in my test equipment, it's easier to change the reference of V1 or the phase to neutral voltages easily for us. So I'm going to use this reference instead of using the V2 or the phase-to-phase voltages. So my MTA is with respect to V23 as 45 degree. And my blinder is opening like this. I have my maximum and minimum angle. So this maximum and minimum angle with respect to my V1 here will be with this respective. So I have 45 degree with respect to V1 and 225 degree with respect to V1 as well. So when I want to do test now, I will be changing my test current phase angle from outside my operating region to inside my operating region. So I will ramp it down from, let's say, 50 degree to 40 degree. So in the middle with 45 degree, it should give me an operation at some level of error tolerance. And the same thing for the other minimum angle as well. So let's go to our setup and do this test. So in order to further explain this setup, I have the relay here with me, B142, and the SVERKER900. I'm connecting to the 3 current channel, I1, I2, and I3. And the 3 voltage channel V1, V2, V3 to the CT and VT inputs of this relay. Usually, if you have this in the field, you will have a test plug to do this connection for you. And I'm taking start and a trip contact, start on binary input 1 and a trip on binary input 2. Now, with this setup, I can do all my tests without worrying about rewiring at all. So, in order to give you a better picture of what's happening inside the SVERKER, let's zoom in. So this is the SVERKER. So the touch screen here, I can use it to change the voltages, the currents, and do all type of testing. And with that one, I hope that's a clear view for you of the touch screen. So now, if I want to do testing for the phase angles, or even before starting doing the phase angle, if I want to do testing for the pickup and timing test, since I see a lot of requests indicating just that, for especially people who are working with maintenance, I need to make sure my phase angles is within my operating region. So going back to the presentation, if I want to do only pickup and timing, I need to make sure that my current is in this region. The phase angle of my current is in this region, and I can do timing pickup test for all phases using this knowledge. So let's start doing that. So I will make my current for phase A and voltage for phase 1 both 0 degree, and you can see the phase diagram here as well. Now you can see my current is in line with my voltage, and it is in our region, which is basically this area here. So, and I can click here and you can see my current and voltage is both on line with each other and in my area. So now if I want to do pickup test, I will decrease my current to a value 0.9, for example, lower my pickup, and directly start injecting this current into my relay. Now the relay should not trip for me. If I zoom out for you, the relay has no LED indicating any tripping here. That indication is from a past event. So now I can basically just highlight this while it's turned on, click on it and it becomes yellow, and I will click this hold button. It will hold the value for me to do this test. So I can increase the current until I get my, yes, my LED now tripped, and this at this value. You can see here my two LEDs tripped for phase A, indicating a pickup on phase A. Now, unfortunately, the device did not hold that because I forgot a very important part, which is the binary input part. I will click on binary input, and I will utilize binary input 1 instead of binary input 2. So let me again show you how that happens. Click on binary inputs, click on binary input 1. I activate this input. It's using a dry contact. For that, I will click on binary input 2 and deactivate it. I will not use it. Let's start the test again. 0.9. I'll click hold again. Now I will increase my current. Now the hold has been recorded, the value at which the relay actually start has been recorded. I can click hold again, and now instead of increasing, I can decrease and do the drop off test. And I got my drop off value again. So I can stop. It will show me the result for the pickup and timing, and there is a cool new feature to show the ratio directly between them and give that in a report. So this is basically a timing or a pickup test in a directional overcurrent relay. If I want to do now timing test, I will simply enable the timer, click on plus time, and select my binary input 2 since it's the trip contact. So I click on binary input 2, activate it, binary input 1, deactivate it, and click OK. OK. And now I'm going to increase my current to a test current, let's say 1.5 of my timer. I click on the play. The timer will run. Once I reach my trip time, the relay will issue a trip, and so 6 seconds I can do another shot at 2 times and the trip time as well. So this is all in a directional overcurrent relay because I has a lot of requests how to do just pickup and timing. We are not requiring to do the whole maximum and minimum angles for this test. So in case your relay did not work, maybe you connected in a reverse direction of your CT or your VT. So in that case, you can just flip the phase angle from 0 to 180 degree. And if it's not working, it will definitely work for you. It was working for me here in 0. So if I click 180 now and I click play, it will not give me trip at all. Not even at 4 seconds like before. And you can see that even the start contact did not light up, indicating that no timer has started at all. So I'm going to stop this test since it will not trip. But just in case it did not work for you, you can flip the angle from 0 to 180 or the opposite from 180 to 0. And we'll fix that issue for you if you are doing a timing and a trip test. Now, back to our main course is the directional overcurrent. This one. For the directional overcurrent, now I want to do the maximum and minimum angle. So again, I need to ramp down my current. I need to make it first above my pickup, so 1.2 amps, and ramp it down from 50 degree to 40 and see when exactly it will give me my pickup value. And the same thing for the other angle as well, from increase it from 220 to 30 and see where is my pickup angle as well. So let's go back. Sorry. Yes. So I'll keep it at 2 amps since 0. So I'm going to first disable the on plus time, put it at 50 degree, click for all phases. Now I'm going to click play. Now my relay did not trip or issue any pickup. You can see it here. I don't have anything activated. So what I'm going to do is I'm going to change the phase angle now. This kit can change the phase angle directly, very easily. Just click on the phase angle, highlight it, and ramp down, go down. As simple as that. Not to forget to get the hold button so I can record the value. I got now my hold activated for me. And then for the other angle, the 220, I'm going to increase it above that. You can increase that much faster by first like this. So I'm going to start from 220 and increase it, round it down to, let me hold the value again. See you exactly. Yes, give me now a trip signal. No, I can stop. It will show me my angles respectively. It's 44.3 and 227.0 for both these two angles. So my original angles was that the ones I wanted to test was 45 and 225. What I actually got is 44.3 and 227. So I verified that these settings are available. It does have a slight error to it, but that's not the main point here. This is how you test these angles. Now, if I want to do the other phases, basically I will just create the same voltage reference for the phases back to 0. So how can we do that? So now I had my V1 at 0 degree. I will make V2 as 0 degree for I2. So click on V2, click 0, and just click this, and it will adjust all the other phases accordingly as well. And I will remove the current from phase 1. I will make it 0. I'll put 2 amps at phase 2. And now start again doing the same procedure. I will do from 50 to 40. I will ramp it down from 50 to 40, and at 45 it should give me a pickup. And also for the minimum angle, I will ramp it down up from 20 to 230, and it should give me at 225 the angle. So let's do that and see. So I'll start at 50. For I2, I click play. I click on I2 and start decreasing the voltage. Let's click on the hold to save our record. Yes, at 44.3. And then I will, for the other angle, I will go to 220. I'm still injecting. Now I'm going to start my hold. Going to increase slowly to find, yes, got the hold too. So I'm going to stop. And I got my two angles for I2 or phase B. It's 44.3 and minimum angle is 226.6. Similar to what I have here. I have 45 for the maximum angle and 225 for the minimum angle. For phase 3, we'll basically do the same thing. Go to V3, make it 0 angle, and then do the same procedure as well. For phase 3, I will make it 0 angle, basically just click 0. And then do here 50 and make 2 amps and remove the current from phase 2. And then ramp the 50 to 40 and 220 to 230 to get the minimum and maximum angle. I hope you got the idea for that. Now, that will be all for our practical session today. Thank you all very much for joining us. I hope it's been a light session for you and a very informative one, and really showcase how easy actually to do directional over current relays testing basically. So now with this, we conclude the presentation and even the practical portion of this webinar. I would like to thank you all for joining us today, and we are ready to take your questions. So the first question asking about the device, I believe it's can we change the frequency of each channel for the injection? Yes, you can change the frequency for each individual channels. So let me just showcase that for you. You can just click on any channel, for example, let's say the voltage channels or even the current channels. I will click here, for example, 49 and this 51 and this 60, for example, and I will just click play, and these things will be generated in this relay. And you can see the relay is actually giving a false trippings because of the different frequencies, 50 and 60 and all, giving this weird behavior because of different frequencies. So yes, you can change the frequency of any channel. The second question we have is directional overcurrent covered in this session? Unfortunately, due to time limitation, directional overcurrent is not covered in this session, but I believe there is application note for the SVERKER900 exclusively explaining how to do directional overcurrent, or I believe even negative sequence overcurrent using the SVERKER900. Please drop me an email on my email showcased here, and I will send you this directly. Another question also regarding, I believe, the SVERKER900 is how about the step change in the current or voltage channel during increment and decrement of the injection values? For the step change, for the increment and decrement, it's in this mode manually, it's controlled automatically via the knob. If you run it faster, it will accelerate fastly, and if you run it smoothly, it will accelerate smoothly. It has its own algorithm. But if you want a steady rate or a controlled rate of change automatically, we do have the ramping tool or the ramping page in this SVERKER900 that you can change the step for the phase angle, frequency, magnitude, whatever you want, in a steady controlled rate at a certain amount for a certain time. So let me showcase that for you. So in the SVERKER900, we have the tool called the ramping tool. This tool. In this tool, we have the rate of change of everything can be changed with a step, a value, dash second. And this change, rate of change, is not a step change, it's a smooth change. all these ROMs are a smooth change. They are not a step by step. So they are really good for frequency relay testings. In case you are dealing with the frequency relays, the SVERKER900 is a very excellent device in that region. And we have, I believe, 2 application notes talking about frequency relays using SVERKER 900. Please drop me an email and I will share these with you, or you can visit our website at megger.com to give this in our technical support section. I believe we are out of questions. Thank you very much, everyone. Or another question just came up. Also regarding the steps in the knob, as I mentioned for you, you can use the ramping tool, and set how much step you want per second. But for the manual knob control, it is using its own algorithm to change the step in it. And it's controlled for more your convenient and accuracy as you balance between these 2 together. I believe we have reached the end of time for this presentation. Thank you very much, everyone, for joining us today. And Sanjay, if you want to do any conclusion in the end, please go forward and do that.
Thank you everyone for attending the session, and please go through the Facebook and LinkedIn link, and you just follow us on the for regular updates, and also register for the upcoming webinars. And uh, thank you everyone for attending this wonderful session, and thank you Ali for giving the presentation. So we would like to close the webinar now, and we will see you in the next webinar. Thank you.
Thank you everyone, and goodbye. I hope you enjoyed this webinar with us.